Oh, I actually forgot my title. Clusters, positivity, and scattering. I think that was it. Thank you. Thank you very much for the invitation to speak here. Just like Yevgeny, I've never met Lakshmibai in person. I applied to be a postdoc with her in my very first round of postdoc applications. It was not successful, so that's that. But I was very much inspired by her work, especially on toric degenerations of black varieties and Grossmannians, which I learned a lot about from my PhD supervisor, Peter Littelmann. So that's kind of my entry into this field. And today, or in these lectures, I'm gonna talk about some applications. So these toric degenerations that I learned about are always kind of in the background of what we're going to see, but we're not going to see them explicitly. I will just give you the plan of what is the content of the lectures. So I'm gonna talk about cluster algebras, a brief introduction. And that's going to be today. Tomorrow, I'm going to talk about tropicalization. Of cluster algebras and flag varieties. And then I'm going to talk about more in detail partial flag varieties and their cluster algebra structure. And all of that really you can think of as being a setup for my last two lectures, which are quite recent varieties math for just one lecture, and not even so much, but the world of combinatorics and representation theory to talk about what is symbol calculus and generalized logarithmic functions. And then in the last lecture, I'm going to present to you two spaces, configuration spaces that are of interest in scattering amplitudes that turn out to be partial flag varieties. And then about the application in scattering amplitudes. So the last lecture is about momentum twister. And spinor helicity varieties. So I wrote some lecture notes and preparations for the program. You can find them on my homepage. Just while writing the lecture notes, I got really excited, and they turned out much longer than what I will be able to cover. So you will find what I talk about in these notes, but there is more material in there. And just like Yevgeny, I would like to invite you to interrupt me and ask me any questions along the way. So then let's start with one. And I'm going to start here with a motivation, that what is for me my favorite motivation of cluster algebras. And it is my favorite because it is very simple, and really all we need to know is linear algebra. So for this, let me define the following for you. If we have a 2 times n matrix, with real entries, then this matrix is called totally positive. If it satisfies the following condition for all indices I and j between 1 and n. The minor of my matrix with indices I and j, so the determinant of the submatrix with columns I and j taken from M are positive real numbers. And this definition, you can easily generalize it to larger matrices. You can generalize it by taking in all minors, not just maximal minors. And then you have the field of total positivity, which is very, it's like a field of linear algebra that is also very well known in applications, computational applications, or in analysis. Well, the main question, if I give you a matrix and I want to study total positivity, is this matrix totally positive or not? So as an exercise, which also serves as an example matrix, and show that it is totally positive. And this is a very, this is an illustrative example in the sense that we have negative entries in the matrix, yet it satisfies my condition on total positivity. So the question here in general is, given a matrix M, is it totally positive? And in order to answer that question, I mean, in this example of 2x4 matrices, it's easy to compute. We have 6 minors. We just compute all minors. We have the answer. But as the matrix grows, the number of minors grows, and it becomes more and more complex computationally to address this question. So we introduced the following notion of a positivity test. That is a set of minors try to figure out, I think I want to write until here, is a positivity test if evaluating all minors in the set gives me already the answer if the matrix is totally positive or not. So if I have Pij of M positive for all Pij in my set delta, then this is equivalent to having Pij of M positive for all Pij. Right, so let's do an example of what is a positivity test. If we are in the case, so in the case of 2x4 matrices, we have the 6 minors but they're not independent. They satisfy a determinantal identity or a Blücher relation. And this is exactly a relation that we can take advantage of if we want to construct the positivity test. So in this case, I would just choose to move this term on the other side. And then I can either eliminate P13 or P24 from my set of minors I have to test. So this implies P13. that this set of 5 out of the 6 minors is a positivity test. Now, why was it important that I move this term to the other side? Because if I would move one of the other terms to the other side, I would have a sign. And as soon as I have a sign in my expression, it's no longer helpful for me to determine if something is positive or not. In generally not, but yeah, it will be called efficient if it is a minimal set. Maybe let me add this. And then maybe in color. Delta is called efficient. So minimal in the sense that I cannot eliminate any of its elements and it will still remain a positivity. Good. So in this small example, I'm really just playing with the indices of the equation. But what I can do here, passing to like a combinatorial representation of a positivity test, is the following. I will take my set of indices that appear in my positivity test and associate to them the edges of a triangulation of a quadrilateral. So here I have P12, P13, P23, P34, and P14. And well, there are 2 possible triangulations of a quadrilateral if I fix a marking of its vertices. So I have another choice here. And this other choice exactly corresponds to the other possible positivity test that I could have chosen based on my relation. And while geometrically these 2 are related by a flip in this triangulation, algebraically they are related exactly by this Plücker relation, which I can rewrite, expressing P24 as a positive combination of the others. So positivity in this expression guarantees me that on the other side, I also have a positivity test. And this geometric model helps me to generalize immediately to matrices of size 2 times n by just considering triangulations of an n-gon and flips that are exactly locally changing the triangulation in one quadrilateral. So in particular, what we obtain from this is a bijection of efficient positivity tests for matrices of size 2 times n and triangulations of an n-gon. Okay. So one important thing to notice here, I've already mentioned, is that for on the geometric side of the triangulations of an n-gon, we have this geometric operation of a flip And we know that it relates all triangulations. So if I have one of them, using this local operation of the flip, I can get to any other triangulation. The flip is defined locally like this. So I can cheat here and just erase all my indices for a moment. And just take these to be arbitrary indices. So I, j, k, and l are arbitrary indices of the n-gon. I have this quadrilateral inside there, and I do the local operation, and it gives me. It's not a permutation. Yeah. So maybe we can do an example in a pentagon. So if this is my pentagon, this is my triangulation, then I have two possibilities here. So if I want to do a flip, I choose one of the diagonals. And any diagonal is part of a quadrilateral. And inside this quadrilateral, I will do the operation. So then I get to, I keep the four outer edges of the quadrilateral and I change the internal one. And yeah, a simple exercise here is to draw all the triangulations of a pentagon and how they are related, which actually gives us the definition of the isosahedron. It's a polytope. That is defined by the following data. So I associate vertices, or I have a bijection between vertices and triangulations of the n-gon. And edges between two vertices are present if the two triangulations are related by a flip. Let's say flip. So this geometric operation of the flip that I have on the triangulation on the side of the positivity test is translates to this algebraic relation between the two sets of the two positivity sets. And this is this kind of combinatorial algebraic structure I have associated to the geometry of triangulations of the n-gon is the basic example of what a cluster algebra is. So yes, there are faces and they're higher dimensional. Actually, I don't know the dimension of the isosahedron to write it down on the board. But yeah, there are higher dimensional faces. So for one example is if n is 5, then the isosahedron is a pentagon. And if it is 6, it is 3-dimensional, and probably that is already your sequence. Yeah. Yes. No, the problem is interesting for arbitrary matrices also. I choose this for like expository purposes because it gets me to a cluster algebra that is of interest to me. But yeah, this can be generalized to arbitrary sizes of matrices, and you can also vary the kinds of minors you want to include in your definition. Okay. So cluster algebra. And in the end, I will get back to this example and show how this is actually the right structure to generalize this observation that we make here. So for my setup, I will always denote by Q a quiver, so a directed graph. I will denote its vertices by 1 to m. And I will split the vertex set into 2, where 1 to n, for some n less or equal to m, are called mutable vertices. And the rest, n plus 1 to m, are called frozen vertices. And I will assume that this quiver does not have any loops, so arrows that start and finish in the same vertex, and also no directed 2 cycles. So in terms of these mutable and frozen vertices, I will introduce the notation if I draw a quiver that the frozen vertices appear in the box. So for example, this is a quiver and 3 would be a frozen vertex. It's just part of my data. And these quivers will be a generalization of the triangulations that I have here. So maybe let me tell you from the start how I associate a quiver to a triangulation. So what I will do is I associate to every edge that is internal or boundary in my triangulation of vertex. And the ones that are associated to the boundary will be frozen vertices. And then inside of every triangle, I will have a triangle of arrows that is oriented clockwise. This is the general picture, but I will add another assumption here. And that is that there are no arrows between frozen vertices. So while to pass from a triangulation to a quiver, I have the general rule that inside a triangle, I get an oriented triangle. But then to comply with my assumption that there are no arrows between frozens, what I will do is simply delete those arrows in the quiver that I obtained by following that rule. Sorry? So inside any triangle of my triangulation, I will have an oriented cycle of the arrows that is also clockwise. So it's clockwise orientation. Yes, yeah. I could, and then I get the opposite orientation. Yeah, this is a choice that I'm making. It's a convention choice, and the other choice will work just as fine. Just be consistent. Yeah, very good. Maybe let me write this down so that it's not just. So if I have T a triangulation, I associate the quiver QT. And this quiver has vertices, or let's say mutable vertices, the diagonal of T. So these are the internal edges of my triangulation. I have frozen vertices, which are the boundary edges of the n-gon. And then I have arrows following this rule. And then lastly, I delete arrows between frozen vertices. Okay. Any more questions? So then the next step, now we've generalized from triangulations to quivers, and our quivers are way more general. We obtained this kind of quivers from triangulations, but of course, quivers that satisfy this definition is a way bigger class. And the next thing is to generalize this local operation of the flip. Yeah. Well, I mean, I'm thinking of this as inside of some bigger. Okay, this is terrible. This is a terrible n-gon. But yeah, so I'm thinking of this triangle as being part of a big n-gon. So this is for every triangle. Okay. Good. So then to generalize the flip, and I should have mentioned, although it's probably known that this theory is due to Milen and Zervinsky. And for now, we're following their first paper on the subject, which is called Cluster Algebras 1. And I think it's from 2003, roughly. Okay, so the next definition is to generalize the flip operation on the triangulations, and it's called quiver mutation. So if I have a quiver Q and K a mutable vertex in Q, so this would correspond to a diagonal in the triangulation, then mu K of Q is another quiver, the mutation in direction K of Q. And it is obtained from my original quiver Q by following 3 steps. The first is, so I will do this locally around K. I focus on my vertex K, and on the first step, I identify all directed to paths. So all directed paths of length 2 that pass through K. So for all chains this form, we introduce a direct arrow from I to J. In the second step, I will invert the orientation of all arrows that are incident to K. And because step 1 and step 2 could create directed 2 cycles or arrows between frozen vertices, in the third step, I just get rid of all of those. So if I take my small example quiver here, I can see what what this procedure does. If, for example, I choose to mutate at the vertex 2. So in the first step, I will introduce a few new arrows. So you can help me with the arrows just to see if it makes sense by definition. Two arrows from 1 to 3. No, I have to take into account both possible ways. And then in the second step, will I turn around all the arrows that are incident to 2? And that's it. In this case, I did not create any 2 cycles, and I also did not create any arrows between frozens because I just have one frozen arrow. So yeah, maybe I leave you 2 quivers to play with. Yes? Yeah, sure. Let's do it. Yeah. So what would I do? Yes, exactly. So if this was my original quiver, sure, step 1 would create me these 2 arrows. But in step 3 now, I would get rid of them. And this would be the result. Yes, thank you. So I also put an example where we delete. Yeah, exactly. Okay, let's do an example. Let's turn my exercise into an example. But you do it. It's still an exercise. Okay, so this is my quiver. You tell me, where do I mutate? Just choose one. Yeah. So let's mutate at 2. Okay, I keep my vertices, right? Nothing changes. And what else? So how many arrows do I introduce where? Let me draw the original quiver and then we can. Yeah, I already started. That was a great idea 30 seconds ago. So, so what are all the arrows I introduce? How many and where? 4, exactly. 4 from 1 to 3. No, because I have 2 times 2 possible ways. So I get, let me write it with a 4. Because yeah. And then I go to step 3 and I want to delete 2 cycles. Oh, and I invert. Yeah, of course. Thank you. Getting ahead of myself. Yes. And now I have a bunch of 2 cycles, right? Okay, I will go bigger. Like this and 4. 4 like this. So there's many 2 cycles. And what I do is I just take them away one by one. So let's say I identify this as a 2 cycle and I get rid of it. And then there's another 2 cycle and I also get rid of it. And I just continue until I reach a point where my quiver does not have any more 2 cycles. So as I don't label arrows, I don't really care what are the arrows I delete. Okay. I think, I don't know actually how I'm doing on time. But great. So what we've done now is we generalized the combinatorics. We generalized the triangulation to quivers. We generalized the flip to mutation of quivers. But what was very important for us here is this algebraic exchange that I had on the level of the positivity tests. So in order to do that, I will introduce algebraic data associated with the quiver and how that changes with respect to the mutation. Yes, let me put this as an exercise. But the solution is in the notes, so don't look at it until you've done the exercise. Quiver mutation generalizes flips in the sense that I have a bijection between triangulations of the n-gon with this combinatorial or geometric operation of flip to quivers ut associated to a triangulation with an n-gon with quiver mutation. Yes. So this is a way, a rule that generalizes the flip. Any more questions on this? We got to see. Oh, that's, I mean, here you choose a diagonal, and this diagonal corresponds to a vertex here. So that is the correspondence. Okay. Oh, this board is so big. It takes like, I don't know how much time to go from one side to the other. Okay, so what is left now is this algebraic layer of exchange relations between positivity tests. And for that, first I want to fix a field that I'm working in. I will call it F. And it's just a field of rational functions generated in as many variables as my quiver would have. So M many variables. And this is my ambient field. So inside here, or with respect to this field, I will define a seed. It's a pair that consists of a quiver, according to my definition, and a tuple of variables. Maybe let's call them primes or something. I have X for my notation here. So Q is a quiver, and X is a tuple of variables, X1 to Xm, that live inside the field, and that satisfy that if I take the field of rational functions generated by those, that is isomorphic to N. So it's a maximal set of algebraically independent elements in my ambient field. And then, yes, equal, yeah. Thank you. Right. So now the generalization of this exchange relation, or this exchange that we had between the positivity tests, is seed mutation. So if I have S a seed, and K a mutable vertex, then mu K of S is defined as the pair mu K of Q and a tuple of X prime variables. So this was also bad. Let's just put A's here. And this tuple xk prime or x prime looks almost like the tuple of x's I had before. I just change one of the variables. And this one extra variable is determined by the following rule. And this is called the exchange relation. So if I multiply xk the variable of my seed with a new variable xk prime. This should be equal to a binomial. So a sum of two monomials. The first monomial is indexed by arrows that go from I to k in Q. And for every arrow, I have one factor that is the variable associated to the vertex. And the second term is indexed by all the arrows that go from k to j in Q. And for every such arrow, I add the variable xj. So it's important to notice that this is indexed by arrows, not vertices. So if I have two arrows between the same two vertices, I will have the exponent 2 appear and so on. And now an exercise is that quiver mutation and seed mutation both are involutions. Questions about that? Oh, yes, thank you. Grammar convention. The product over the empty set. Where? Empty product. Is one, yeah. Okay, good. So maybe a second exercise is that the previous exercise on quivers associated to triangulations, this bijection also holds if to the triangulation I associate, let me see, maybe I can add it in. I'm kind of greedy with my board. No, I cannot. So let's do an example. If T is a triangulation, then QT with the tuple of variables consisting of exactly the PIJs I would associate to edges of the triangulation is a seed. And now the mutation, the seed mutation here generalizes the exchange relations that we saw coming from the correlation. Okay. No, they include frozens. Yeah, exactly. This is always only on mutable vertices. Yeah, totally. I'm not really following my notes. It's a bit sad for me, not for you. Okay, so right. Then I will give you the definition of a cluster algebra straight away. Yeah. The cluster algebra associated with a seed S is the following. I will start from my seed and I will just do all the possible mutations that I can in all possible directions. And I will collect all the variables that appear along the way. So maybe I should say that a tuple of just the cluster variables of a seed is called a cluster. And its elements are called the cluster variables. So I will collect here all seeds that are mutation equivalent to my seed S. And then I will just take all the variables appearing. And I take this as a subalgebra generated by these elements in my ambient field. Yes, yeah, absolutely. Thank you. Yeah. Okay, let's do an example. I will start with the first non-trivial quiver, the first, well, more interesting non-trivial quiver with 2 vertices and 1 arrow. And in order to save a bit of space when writing a seed, what I will do is I just write the variables at the vertices. So I have this notation, x1, x2, for a seed with this underlying quiver. And now I will start doing my mutation. So if I, yeah, when they're called mutation equivalent, when there exists a sequence of mutations starting here, that gives me this quiver. So where q prime x prime is mutation equivalent to qx if there exists a finite sequence of mutations. From qx to q prime x. Okay, great. So let's do this exercise together, if you want. All we need to remember is this exchange relation. So I will start with mutation in direction 1. So following quiver mutation. Did I lead it? No, it's over there, right? Yes, it's over there. So my quiver is very simple. There's no 2 paths. So step 1 goes away. Step 2 applies. I change the orientation. But that's it. Step 3 does not apply. And then according to my seed mutation, I will replace this tuple of variables. And in this tuple, I will only replace the variable of the vertex we're mutating. So I will keep x2, and I replace x1 by what? Empty product is 1, exactly. So my Bengaluru 1. Exactly. And this is then a new cluster variable. And then I continue, and I keep the So I continue in direction 2 because it is an involution. I don't have to go back. Again, the orientation changes. And then on the right-hand side, as a new variable, well, I get the same formula, but now applied here. And I can simplify this like that. Okay, and I continue. So now the next step is already a bit more involved because I will have to, well, this appears in my product and I have to divide by this one. But so I will give you the answer straight away in this case. And if you do the exercise, you will notice that there's a simplification happening. And the new variable I get is this one. Let me check my exam. This phenomenon that computations on the board are not possible. Okay, so this is my new variable, and I continue. And there's another surprising simplification that turns, after mutation at this vertex, turns this variable into just the variable x1. And then I do one more mutation, and this variable mutated is x2. And there's one thing that I do also just to simplify, to save time, is that I identify two quivers or two seeds if there's a permutation of the vertices that identifies them. So here I have that these two are identified, and yeah, because there exists a permutation, that sends one to the other. Okay, so this is my example. And I can also add the cluster algebra in this case. So my cluster algebra is associated to the seed inside my field of rational functions. And I can always assume now, given the definition of a seed, that the cluster of my initial seed is the set of generators. And this algebra is generated by all the variables that appear in any of the seeds. So it's generated by x1, x2, and then the other 1 plus x2 divided by x1. Okay, great. Okay, I have a few more minutes, right? So then I think I will give you two more definitions, just taking advantage of this class as the class of definitions, so that we can then advance to more interesting things in the rest of the lectures that I will use later on. So so you're looking for a presentation? Yes, yeah. I mean, we can always get the presentation of a cluster algebra. In this case, it is easy because I have a finite set of generators. So I can get a presentation of this cluster algebra by sending it to the polynomial ring with generators in correspondence. Let me call them maybe these, Z1, Z2, until Z5, sending xi to zi, where this is x3, x4, x5, and the kernel of this map is my set of is my generating ID. Oh yeah, sorry. Thank you. Yeah, and the relations in this case, yeah, they are they are essentially Plücker relations just by setting all these 5 cluster variables are in bijection with Plücker coordinates or minors ij, where I and j are not adjacent. Modulo 5. So this ideal is the Plücker ideal, where I specialize all the pi I plus 1 to 1. Okay. Yeah, so I wanted to define one more thing. And that is, to every cluster variable, xk, I associate the following. It's called a y hat variable. Y hat k. And it is pretty similar to what's on the right-hand side of my exchange relation, just that it is a rational function where, or like a Laurent monomial, where I take one of these terms and divide by the other. So in particular, if I have xk prime, the mutation of this variable, then the corresponding y hat variables are just inverse of each other. So let's write this y hat xk. And this is a notion that I will use. This gives rise to the notion of y seed in Fomin-Zelewinsky's work, or it's also an example of a coefficient pattern, if you've heard of this before. But for us, it's enough to know that we have these kind of variables associated to our cluster variables, but that they're not independent. They satisfy relations that are induced by the exchange relations. And then lastly, I want to give you the notion of a cluster subalgebra. So there's like a general non-trivial question, like if I have 2 cluster algebras, how can I say if one is a subalgebra of the other? Because of course I would want, if I take a subalgebra of a cluster algebra, I would want this also to be a cluster algebra. And if I just take any subalgebra, this combinatorial structure will just break. So there's one combinatorial way how to create subalgebras that are also cluster algebras, and that is via the notion of a restricted seed. So now I better copy my notes for notation. So if I take Q a seed, and Q0 here denotes the vertex set. Okay, I'm sorry, this is not visible in the video. Q0 is the vertex set. So this is a seed, and I take what is it called? A partition of the vertex set. Such that there are no arrows between the mutable vertices that belong to I. Yeah, and vertices of J. And then I take Q prime be the quiver that I obtain from Q by deleting all the vertices in J. Then Q prime together with the set of variables corresponding to its vertices is called a restricted seed. And they are just all the arrows that I have between the arrows of I, arrows that I have between vertices in I. So the condition here is that there's no arrows between the mutable vertices of I and J. So there can be arrows between vertices of I and frozen vertices in J, but this separates the mutable vertices. And then I can just delete all the vertices that are in J. I keep, as a full subquiver, I keep all the arrows, and this is Q prime. And if I now start with this restricted seed, then I get an algebra, cluster algebra, that is naturally a subalgebra of the one that I get from the original seed. And the cluster structures are compatible in the sense that whenever I do mutation here, there's a mutation in the original cluster algebra that corresponds to it. Yeah, Q0 prime, so this is capital I, yeah. Okay. So maybe I spell this out and this is where I stop. Or maybe I stop actually. I stop. Thank you. That's fine, yeah. And then, I mean, then you're flexible. You can, if you want, you can also say that you keep the frozen vertices in J, or you don't. Like, yeah, there's a bit of flexibility. Also, I can create this situation artificially by just if I just split my vertex set, and I do have randomly, and I do have arrows between I and vertices in J that are mutable, I can just freeze them. So I can do like a mix of freezing and restricting, freezing and deleting, and that will give me the notion of a sub pattern, a cluster sub pattern, and a cluster subalgebra.